This is the first of 12 presentations on the structure and property of organic molecules. Richard Feynman once said, and I'm paraphrasing, "Figure out what you want the students to know or do, and the method will more or less present itself." David Klein, a popular author for organic chemistry textbooks, really started his career in writing, as far as popular writing or popular with the publishers, with his little book called Organic Chemistry as a Second Language. And in that book, it was unique in that it started with not atoms, the smallest units within any of the molecules we talk about in chemistry, or compounds we talk about in chemistry, but he started with the drawings of organic chemists, the molecules, these two-dimensional representations of a three-dimensional world of molecules, distinct packages of atoms, so many and in such a place in space. These atoms together make a molecule. Now, it's hard for students or folks outside of the world of organic chemistry to make sense of these drawings. But that's where it started with David Klein in his book, Organic Chemistry as a Second Language. It started with these drawings. These drawings, these what we call skeletal drawings or representations or bond line representations, is what you find throughout the literature in organic chemistry. It's the starting point. So this is a good place to start if we want to take the advice of Richard Feynman and talk about organic chemistry. And what do we want folks to be able to do in organic chemistry? We want them to be able to speak the language that's centered around these drawings. This is the language that organic chemists use to talk to each other about the molecular world and how it's changing or how they make it change. They draw molecules. They draw atoms bonded in such a way as represented in this drawing here. These presentations, these 10 to 15 minute presentations, do not bring you to the front edge of the vast front edge of research. No, it does not do that. What it does is it takes you under the waves, so to speak, or the ocean, to give you the basic concepts or flow of ideas that chemists sort of start with as they look at these molecules that are represented on the surface of this ocean of reactions and research that's going on. It's a very volatile world, and it can be to sometimes nonsensical movements within this world or this body of knowledge or this field of study we call organic chemistry. But it all underneath starts with understanding structures. Let's dive under then the wave or the vast ocean of organic chemistry, the new world that you might be considering here, and let's just start with how do chemists think about structures. So that's where we'll be going with these 12 recordings, these 10 to 15 minute presentations. We'll look at first with this one, drawing structures. What are the basic rules for drawing structures? We'll move into very quickly looking past letters and lines, seeing these lines here as more than just two electrons between two atoms that are so far apart. No, we'll see electrons through orbitals. Then we'll look at drawing resonance forms. For this purpose, resonance forms are very, very important in that it helps us to see where things are rich or poor in electron density, who's partially negative, who's partially positive within these structures that are represented. Any of the molecular structures that are represented in the vast ocean of organic chemistry. We can make sense of those structures by drawing resonance forms or understanding how to do that. To find partial charges, and that leads right into understanding where you would have protons. This is a proton that would be most acidic. They would be bonded to atoms that have a partial positive charge, something that's going to be deficient in electron density, so it'll draw electron density towards itself if it's partially positive. That helps us see what protons would be most acidic. Or if we're wanting to find basic sites, These are electron-rich sites, sites that would be in excess of electron density within this molecule. And you say, I don't see it. Well, that's the point of these 12 presentations, is to help the viewer or person looking into the world of organic chemistry make sense of drawings like this and see or unpack a wealth of ideas or concepts that lie under this drawing. This is shorthand for organic chemists, but when they look at these letters and lines, they see a whole lot more than just wedges and dashes and lines and letters. They see structure. Then we'll finish with conformation, so to speak, of the molecule, what it looks like in three-dimensional space that's not locked in, then conformation that is locked in, how things are oriented in space. And these can be difficult for students, and it's very advisable that you use a model or a kit to help make sense of the conformational world of organic chemistry or the stereochemical world of organic chemistry. So let's get started, though, in trying to just get to the basics of drawing structures, valid structures for any collection of atoms, carbons being the king of organic chemistry, but some number of carbons, hydrogens, oxygens, nitrogens. How do we get started? So let's just imagine, let's say we had a bag of carbons, oxygens, nitrogens, and hydrogens. We would have to think about, how do I start putting together with those specific atoms, those units, how do I start putting together valid molecules, organic molecules? Well, we would go with some ideas we've learned from general chemistry, and let me just sort of start with one. If I gave you a carbon and 4 hydrogens, you could propose, because you know the number of electrons that carbon has around it as an atom, it has 4, and you know that it likes to go to the octet state. That's a favored state for second row elements like carbon, like nitrogen, like oxygen, and fluorine. These like to have 8 electrons around them. So they would bond with hydrogens, which can only have 1 bond off of it. It does not go to an octet state. It goes to a full valence shell having 2 electrons around the hydrogen. It does that by bonding once. So carbon bonds 4 times and hydrogen bonds 1 time, and so we could build what's called methane. And this would be a valid structure. But we can draw others that are involving a greater number of carbons within the molecule and hydrogens off of those carbons. So there's a lot of different molecules that we could draw if we had an abundance of carbons, hydrogens, and even oxygens and nitrogens thrown into the bag. So that's the skill we want to be able to have, is to see what structures could I draw if I had so many carbons, so many hydrogens or oxygens or nitrogens in the bag. So let's do this. Let's propose that we don't count the number of atoms in here, but we determine the units or the number of atoms within each molecule. So for this one, for example, we would say CH4. We have 1 carbon and 4 hydrogens. This is not a representation of the molecule, but we're just saying this is the number of carbons and the number of hydrogens. So we could expand on that and say, what if we had 4 carbons, not just 1 carbon, for every molecule? In one molecule there are 4 carbons. In one molecule, again, this distinct picture we said of the organic world, some molecule has 4 carbons and it has 8 hydrogens. How could we start proposing structures that have this, what we call molecular formula, number of carbons and hydrogens? This is not representing a particular structure. That's very important. Molecular formulas are just telling you how many C's, H's, and O's and N's you have within the molecule. How would we start drawing valid structures? Well, there are 3 steps that you need to take. So I'm just going to write these steps out, and then we're going to use those steps and we'll be done. So the first step we have to take is we have to determine the degree of unsaturation, or degree of hydrogen deficiency is another word you might hear. Determine the degree of unsaturation. That will explain a little bit here as we go. Just going to really be related to the number of pi bonds or rings that have to be in the structure. In other words, it's sort of a rule we can look at, and it has to apply regardless of the structures you draw for C4H8. We can determine the degree of unsaturation that each molecule has to have if it has this number of carbons and hydrogens. Then we can move on to drawing all what I call, frames, not FAMs, frames. All the, like in a house, the building of a house, the 2x6s, the sill plate, the concrete, that's really the frame. And then you hang off of that the sheetrock, the vinyl siding. You hang things off of it. This is what we have to find out, is what is the connection of carbons, the interior elements, their framing. What kind of framing can we have? And then last, add in pi bonds halogens. Halogens. Now, why are they considered last on the frame? Because halogens can have how many bonds? Take a cup of my coffee here. How many bonds can halogens have? I hope you were saying just one. It's not showing up here, but fluorines, chlorines, bromines, anything in those that column where bromine and chlorine and fluorine sit can only have one bond. That's the valency, so to speak. They have just one bond off of them in neutral structures. So let's go ahead and take this C4H8 with our three rules. What were they? Determine degree of unsaturation, draw the frames, add in pi bonds and halogens. If we use these rules, these steps, in this task of drawing structures, we can have success. So let's go ahead and apply that to this C4H8. And just so we know what we're drawing as different structures that fit this formula, what we're drawing are what we call constitutional isomers. That are compounds or molecules that have the same molecular formula, in this case C4H8, but different connectivity. I'm not talking about where things are in space, but who's connected to who. That's and as far as atoms go, a different connectivity. So let's go ahead and go through our three steps. We said determine the degree of unsaturation. To do that, what we're trying to determine is the number of pi bonds or rings. And what we know is if we had no pi bonds or rings, then the number of hydrogens to the number of carbons would be 2n plus 2. But anything short of that number, so let's take this 4 as n, times it by 2, and add 2, that would be 10. Well, we certainly don't have 10 hydrogens. We have 8. So what we have is 10 minus 8. So we're short of that number. And you're always going to be short by a multiple of 2. So we take that difference, 2, divide it by 2, and we have what we call 1 degree of unsaturation. 1 degree of unsaturation. And what we mean by that is that we either have one ring or one pi bond. Now the easiest way to think about this is to just consider, let's say, 4 carbons. Let's say these are the carbons in the middle and we're kind of considering the frame. If I had hydrogens on these carbons on the end and I wanted to connect these two ends to make a ring, I would have to take off one hydrogen from this end, one hydrogen from this end to close the ring. You would have to take away 2 H's to get these carbons to bond to each other. You would have to, in other words, take them, whatever they're bonded to now, in the linear form, non-cyclic form, you'd have to break off a bond on this side and break off a bond to a hydrogen on this side so that you could make the new bond. So you're always going to have to remove 2 hydrogens for every ring that you make. It's the same idea with pi bonds. We'll find out that you always have 2 hydrogens you lose for every pi bond that you make. Alright, so that's very important. So that's our first step. The second was draw all possible frames. I'm going to go a little more quickly here with this step. We know we don't have any N's or O's. We have 4 carbons. And we know we have the ability to consider rings. So we can do the simplest thing first, is to consider those structures without rings. And that's just in a what we call linear form, 4 carbons in a line. We have 4 carbons, so we could connect them in a line. We could also lift this carbon off the end and put it on the interior. See what I'm saying there? Do you hear it? Connectivity. I could connect this carbon on the end of 3 in a line and put it off the middle carbon of 3 in a line. So we could propose, and I'm just drawing again, not final structures. What we're drawing here are just frames, just the interior elements. So 4 in a line, 3 in a line, 4 in line. That's the easiest. Put them all in a line, 3 in a line, and 1 off the middle. And then last, because we have a degree of unsaturation, you have to consider the biggest ring, 4 in a ring. And can you guess what would be the next ring we could consider? I hope you're saying 3 in a ring. And you say, well, where do I connect the other 4th carbon? I know I have to have 4 in each of my frames. Where do I connect it? Well, think of it this way. The molecule doesn't know left, right, up, and down when it's in solution. It's all relative. So I could put it off of any one of these 3. It's equivalent. So just for the sake of space, I have a little more space here. I could say it's off of this carbon here, but I could have drawn it here or here. We have freedom to draw because it doesn't matter where you put this 1 carbon on the cyclopropane ring or 3 carbons in a ring. We'll get to naming later, but these are my 4 frames. These are my 4 frames that I have now. And now what I want to do, that's the second step. We had the degree of unsaturation. That told us we have these 2 frames to consider. Now we want to do is move to the last step of the 3, and that is add in pi bonds and halogens if we have them. Now, do we have halogens with this molecular formula? Halogens, halides, fluorine, bromine, fluorine, chlorine, bromine, iodine. Do we have those? I'm going to take another sip of my coffee. We're almost done. No, we don't have any. I know I have only C's and H's, so all I need to do for this molecular formula onto these frames is add pi bonds. Now, which of these 4 frames need pi bonds? Do we need to put pi bonds in for these 2 frames? I hope you're saying no, because we already spent, in a sense, our degree of unsaturation by making these 2 rings. Now, this still needs its 1 degree of unsaturation. This one and this one still needs its 1 degree of unsaturation. We're going to have to add in pi bonds for these 2 frames. So let's finish this one and move on to a second application, and we'll be done with this discussion of drawing structures or building structures from molecular formulas. And we're on that section now where we're taking it from the frames. We have our 4 frames, the non-cyclics with no degree of unsaturation yet. These need pi bonds. And these 2 are with their degree of unsaturation, so we can go ahead and draw the Lewis structures for these 2. That would be the easiest. And I'm going to go ahead and let's keep this in the rules. Let's draw everything out. Lewis structures can be very difficult to look at because there's just a lot of detail that we can leave out when we get to skeletal drawings. This is a more shorthand notation of the structure. Drawing it all out here, I'm going to give myself a little more space. How many hydrogens do I add in for each of these carbons? How many hydrogens have to be added in to this frame to complete the structure? Because we can't just have carbon with 2 bonds off of it. How many bonds does carbon have off of it? Stop me when I can hear you when you shout it out. There's 3, sorry. I hope you just shouted. 4. So we have 2 more bonds off of each carbon, and we only had hydrogens in our molecular formula, and it does work out C4H8. So you don't have to worry, just add in your hydrogens. If you get the framing right, you can add in your hydrogens and be done. So that's with these 2. Just move to what the skeletal structures look like. Now, skeletal structures are shorthand notations of these Lewis representations. They're simpler, they're easier to look at. And this is the rule. You don't draw hydrogens unless they're off of O's or N's, oxygens or nitrogens or sulfurs or phosphorus, anything other than a carbon. So here we can really abbreviate things and say this is what I have. Oh, that's simple. Yeah, it's simple. It's just these kinks represent the carbons, and this end represents a CH3 group. So you'll sometimes see folks just write it in CH3. Sometimes they'll leave it as just the true skeletal drawing. But that's it. I drew it kind of small there. And you just draw it. And this one's looks like a square. So well, no, it's not a square. In the language of organic chemistry, that's cyclobutane. That's four carbons in a ring. Now let's go to the others that were a little bit more difficult. These two. What did we still have to add in for these two? I hope you're saying pi bonds. So we can add the pi bond in where? For this first one, we can add it, and hear what I'm saying, between the carbon on the end and a carbon in the interior. Let me say that again. A carbon on the end and a carbon on the interior. That doesn't mean I'm here instead of here. It can be either of these two positions. They're equivalent. Because again, there's no left-right within the world of organic chemistry. So I'm going to start off by putting it on the, I guess, left end. We'll just kind of follow sort of the English language, left to right. And then I'm going to add in the hydrogens. See, it took me some time to do that. Now I can also add it in. Let's make sure we got everything square. Carbon should have 4 bonds, and yes, 1, 2, 3, 4. This has 4 bonds off of it. Looks like we're good there. Now we could say I could have put the pi bond not here. Again, that's the same as here because it's carbon on the end connected to a carbon in the interior, and there's no way to know which side you're talking about. But I could have also said a carbon on the interior to the carbon on the interior. That's where the pi bond could have gone. So let's finish this out. And I'm using lines instead of dots for these Lewis structures. And again, I don't have a non-bonding pair with carbons and hydrogens. So these are the two Lewis structures that fit this frame. We're adding in the pi bonds on the end to the interior and then between the two interior carbons. And now again, you'll see that the skeletal drawings are much easier. Bam! Done. That's this one. Let's do this one. Ready? Go. Bam. Done. That's why it's so much easier. And you say, well, I don't understand what you just drew. Remember, these are ends. They're carbons. This is a kink. That's a carbon. So there's an H off of that that's really not shown because it's off of a carbon. We don't draw H's off carbons in skeletal drawings. And then this end has 3 hydrogens. This has a carbon added and 3 hydrogens off of it. Now we're almost done. Now let's finish with this one and say, where do we put the pi bond? We know it needs one because it doesn't have a ring right now. We need 1 degree of unsaturation. Where do I put it? Listen to what I'm saying here again. Let's connect. Let's put the pi bond between an exterior carbon and the one interior carbon. Do you notice that could be 3 positions? Here, here, or here. They're all equivalent. It doesn't matter. So let's go ahead and pick the north here. This carbon here at the top. So we're going to put a pi bond between these 2 carbons. And again, this carbon here has to have 4 bonds off of it, but we're not involving it in the pi bond. We could have. We just picked one of these 3. And we are done. Let's make sure we have 4 bonds off of each carbon. Yes, yes, not 5, not 6. 1, 2, 3, 4. This is satisfied, and now we could draw the skeletal drawing for that, and we're done. All right, one more, and this presentation will be complete. Let's take on, and we're going to go a little more quickly here with this one. It's a simple one. C3H5Cl. Now, how do we determine the degree of unsaturation? We take that 3 times 2 plus 2, so that would be 8 for this one. And we take the number of hydrogens and halogens. Why? Halogens replace a hydrogen in the sense that 1 bond is what a hydrogen has to the molecule, or in the molecule it has 1 bond. So does a halogen. So if you want to get a halogen into a structure, you have to take 1 hydrogen away to get a halogen in. So it's like a hydrogen in the sense of this determination of degree of unsaturation. Index of hydrogen deficiency is another term you might hear for this. So we're going to add 5 and the chlorine with 1. So that's minus 6 divided by 2. So 8 minus 6 divided by 2, that's 1. So for this structure, we also have 1 pi bond and or 1 ring. So again, we consider halogens are considered as hydrogens. So chlorine, bromine, fluorine, we use them in the count to determine the number of, we say, sort of hydrogens. It can substitute for that. And for every degree of unsaturation, we said there is a pi bond or ring present. So we have to build structures that have 1 ring or 1 pi bond. So let's draw our frames. We only have 3 carbons. Halogens are on the outside. They only have 1 bond. So the simplest frame is 3 in a line. You could say, well, I'll put 2 in a line and have 1 off of this position here. This going to the top. 2 carbons in a line, and I'll put this one going to the top. We're not talking about orientation with framing. We're talking about connectivity. This would still be connected to this carbon here on the end. And you say, well, I'll move it over here then. Well, it'd still be connected to a carbon on the end. It doesn't matter the orientation in space. It would still be 3 carbons in a line. So we're done as far as non-cyclic structures. Now, cyclic structures, this is the best we can do. 3 in a ring. So these are our 2 frames. Here, where we need to add a pi bond, you say, well, where do I add it? Here or here, it doesn't matter. So we can put the pi bond in, and we just start adding the hydrogens in. Or we can consider the ring structure. We have 3 carbons, so we're going to go ahead, and I apologize, we're going to have to, I forgot, we don't have 6 hydrogens. What did we say replaces it? A chlorine. So we can put it in one of 3 positions. We can put it on the carbon on the end that's in a pi bond, the carbon in a pi bond that's in the middle, or the carbon that's not in a pi bond and it's on the end. So these are all distinct. So we can sub it out. I'm going to start with, just makes sense, left to right. So you want to erase that hydrogen and put in chlorine. But we could have also considered this chlorine to be here, because that's a different position, a different connectivity. Or we could have placed it, last one, we could place it on this carbon. You say, well, which one of these 3? It doesn't matter. We're not talking about orientation. We're just talking about where it's connected. That's constitutional chemistry, where it's connected. These give us constitutional isomers. These 3 now are different, because I needed to add in the pi bond. I remembered that, but I forgot I need to get that 1 chlorine in. It can go, we just want to consider, maybe just put the pi bond here, because it's got to be part of the, this is the one structure we build off. We can put the chlorine here, here, or here, and those are all different positions. All right, our last one was this this cyclic structure. And where can we put the chlorine? Any one of these 3 carbons. They're all equivalent. So I'm a little bit outside of my box here. But we have 2 hydrogens off of, oops, I forgot my bond here. We got 2 hydrogens off of these 2 carbons, and then a hydrogen and chlorine off of this carbon to the north. But we could have put the chlorine here. We could have put the chlorine here. It doesn't matter. Now let's get this quickly and we're done. Let's see how fast we can draw all skeletal structures that have this molecular formula, C3H5Cl. And what we did is we worked through the steps. We determined the degree of unsaturation. That was 1. We knew we had to consider frames then that have rings or a pi bond. These were the only 2 that we could have. Then we put the pi bonds and halogens in. We put the pi bonds, I kind of went back to this framing, and we put the halogens, that chlorine, in. Let's draw this quickly. So we draw the chlorine off of this carbon, but it also can be drawn off the interior carbon that's in a pi bond, or it can be drawn off of the end carbon that is not in a pi bond. This one here. So we see those three different positions. And then last. That took me all of a minute. Well, that's it. Well, that's the way in which you can take a molecular formula and draw valid skeletal structures.